Hi everyone, unfortunately I realize there are only 2 more days where I am going to give the lecture in this semester. On the bright side, your project presentations are coming up soon and I'm really looking forward to seeing how your projects turned out. But my plan for these remaining 2 lectures is to talk about autoencoders, mainly today, and then about generative adversarial networks on Tuesday. And so we'll start by looking at autoencoders, what autoencoders are and why they are useful, for example, for data compression. And then I will show you a simple example of a fully connected autoencoder. So this is very similar to multilayer-perceptrons, where we have fully connected layers. And as you remember from the convolutional neural network lecture, it's useful to have these convolutional layers when we work with image data. So we'll extend the fully connected autoencoder concept to a convolutional autoencoder using convolutional layers and transposed convolutional layers so that we can also compress image data more efficiently. And pay particular attention in this section because we will reuse this idea of the convolutional autoencoder when we talk about generative adversarial networks for generating image data next lecture. And at the end of this lecture, I will also show you some other types of autoencoders. However, I'm really trying to keep that section short so that I don't have too many slides this time because, like I said, we are nearing the end of the semester. And I think it's also important to have some fun, so we will also look at some code examples this time at the end of the lecture. So with that, let us get started then. I'm going to call it a short introduction to autoencoders, because like with any topic we covered in deep learning, there's always more to talk about. However, to keep it brief, I kind of summarized the main points in these slides, and I think it's helpful if you download them up front from GitHub like always, so you can take notes on your slides when you watch the video. So I will start by showing you some examples of autoencoders before I actually define how autoencoders work. So just to motivate you a little bit to show you what you can do with autoencoders. So here in this example, the researchers took a noisy audio example or speech example and used an autoencoder here. So this would be the autoencoder. Don't worry about it yet. I will explain how that works later. And you can see what you can see here is that from the noisy image example, we go to a kind of cleaner version. So here you can see there's a lot of these specs here, and this one looks a little bit cleaner. But yeah, of course, it's an audio example, and looking at the audio spectrogram really doesn't tell us that much because we can't hear it. So maybe a better example showing you how an autoencoder works is showing you an image example. An example of a medical image here. So what the researchers did here, they were taking a noisy version of an image, and so at the top this would be the original version, but you have to pretend that during testing time you don't have this original. All you have is the noisy version. So and then the researchers use an autoencoder to make or denoise this noisy image. And you can see the denoised version here. I mean, this is not very sharp, it's a little bit blurry. It's not as great as the original at the top. However, you can see going from here to here, that's definitely an improvement. So you can see at least the contours of the image. So that would be one application of autoencoders. Of course, there are also other models that can do that, but I think that's not too bad to motivate the example why autoencoders are useful. I should clarify the models or examples I've shown you before. These were examples of a special type of autoencoder called denoising autoencoder, so that there's no confusion. We will first later talk about the general autoencoder, and then also in the end I will mention the denoising autoencoder again. In any case, on this slide I'm showing you an example from my own research. We call this the semi-adversarial network model, and I don't want to go into too much detail about this model. However, part of this model is also a convolutional autoencoder, and the whole goal of this model is to selectively hide information from face images, so-called soft biometric information. So we want to still maintain the utility of the images, for example in face matching applications, for example security scanners. However, at the same time we don't want to allow automatic data collection of data that the users or people in the images don't have agreed upon. For example, extracting the gender or age from the images. So on the right-hand side, I'm showing you a nicer image from a recent follow-up paper. This is from a preprint that we recently uploaded to arXiv this year. So here are shown some examples. So for example, this would be the original input image, and this version would be an image where the gender information is hidden. That means the image still looks like almost the same, so people can still recognize this person. However, now algorithms that can extract the gender are not able to do this confidently anymore. So we fool the automatic algorithms that can extract gender information, and the same here for age. So these are versions of that image where the algorithms cannot extract the age information anymore, and also one for skin color. So why is that useful? So in this case, that is useful because we can selectively hide information that the users don't want to reveal. And there was just 2 days ago a survey result posted here saying that about 52% of US adults said that they decided recently not to use a product or service because they were worried about how much personal information would be collected about them. So one application of our project would be that you can still upload your image. However, you would be less concerned that automatic algorithms, data mining algorithms, could extract your personal information from these images. But yeah, I don't want to go into too much detail about the particular research here. I just want to show you that would be another example of using an autoencoder. In particular, a convolutional autoencoder, which we will also cover in this lecture. The lecture into 4 parts. So the first part will be more general about dimensionality reduction, just to give you some motivation of what dimensionality reduction is and why do we care. So in the second part, we will then introduce the fully connected autoencoder, which is a type of autoencoder, the simplest type that uses fully connected layers, similar to a multilayer-Perceptron. And then we will extend that concept to convolutional autoencoders, and then also briefly talk about other types of autoencoders. Of course, we can devote one whole lecture to each type of autoencoder, but this time I also want to cover more of the code examples that I uploaded to GitHub. So in that way, I will keep the last section a little bit short, and then we can also look at some code examples. So let us start by revisiting unsupervised learning. I talked about unsupervised learning at the very beginning of this course, and we haven't really used unsupervised learning since then. So most of what we've done was supervised learning. Unsupervised learning would be practically the opposite of supervised learning, because in unsupervised learning, we learn without having a class label or target variable. So we don't have a target variable here. We only have the observations. So what are some of the applications and goals of unsupervised learning then, if we don't want to predict anything, if we don't have a target variable? So one common application would be finding hidden structures in data, where you extract useful information from a very high dimensional data set. And that can be also used for data compression, for example, where you want to store data on a certain storage space, but you don't have enough capacity to store all the features, for example. I remember listening to a podcast where I heard people in astronomy use that approach for filtering out information from high resolution telescopes, because these telescopes, they create petabytes of data each hour or each day, but it's in any case too much to be stored on a hard drive all the time. So they use certain techniques to extract useful information from the data. Or clustering would be another common example, where you have similar, for example, customers, and you want to find out who are the same customers, so you can design products for these certain subgroups. And that is also related to retrieving similar objects. For example, if you have a number of Netflix customers and you want to make recommendations, so you can either find similar people who have the same viewing behavior, so you can look at what other similar people viewed on Netflix and make recommendations that way. Or you can also look for similar movies. So if someone liked a certain movie, you can also find new movies based on similarity, using some features about the movie. And exploratory data analysis would be another application of unsupervised learning, where you use techniques where you don't necessarily need to predict something, but you rather explore the data set. And maybe one of the recently most exciting applications of unsupervised learning is generating new examples or data points. So generative adversarial networks would be one example where you generate new data points. And I would say this is particularly exciting because it makes really for nice images. So it's always exciting to show something that was generated by a neural network. So unsupervised learning technique that you have maybe heard about already in other statistics classes is principal component analysis, or PCA. And the goal of PCA is finding the directions of maximum variance, which can be used for dimensionality reduction, or you can also call it data compression. So imagine you have a two-dimensional data set, x1 and x2. Of course, this is also a very, very simple example. In practice, you would have a way higher dimensional data set. For example, if you think of MNIST, that would be 784 dimensions. However, it's difficult to show higher dimensions, so we have to unfortunately stick with 2 dimensions in our visualizations. In any case, so here we have 2 features, x1 and x2, and what we want to do is we want to find the maximum variance first. So that would be, in this case, this direction, which we call PC1, so that is the first principal component. And then we find the second direction of maximum variance, given the constraint that these vectors are, or directions are orthogonal. So there's a 90-degree angle to them. And that would be PC2. And then after we identify the directions of maximum variance, we transform the features x1 and x2 onto the directions of maximum variance. So we project them onto these principal components. So the data points, these circles, we project them then onto the principal components. In this case, it's a linear transformation. So here it's a rotation. And so this would be PC2 and PC1, where PC1 is the direction of the maximum variance and PC2 is the direction of the maximum variance, given the constraint that it is orthogonal to PC1. And that is, in a nutshell, basically what principal component analysis is doing. It's a linear transformation technique. So how is that useful? So what we can then do is we can drop dimensions in that new subspace. So usually we want to keep the directions with the highest variance if we have multiple principal components. So here in this case, we keep principal component 1 because it has the maximum variance here. And this is simply then squashing the data onto this one dimension. And this is useful for compressing data while retaining most of the variance, assuming the variance is most of the useful information in the data set. I should mention this is an unsupervised technique, so it's not aware of any class labels here. However, it may be useful for classification. So for example, if these were examples from class 1, and these are examples from class 2, if I would then extract principal component 1, it may look like this, where we have the circles on this side, and then the pluses here on this side. And then we can have a linear classifier separating those two. Of course, this is only a very simple example. In practice, we would have way higher dimensions. And here in this example, for example, it would be not necessary to store feature x1 and x2. Of course, I can also fit a classifier here. But again, if you have a very high dimensional data set, classifiers may suffer from the so-called curse of dimensionality, where it's sometimes useful to reduce the number of dimensions. And now if you have a high dimensional data set, you may ask, okay, how many principal components should I keep? So this is kind of arbitrary. You have to kind of look at how much variance is retained by them. And we are not going into too much detail about principal component analysis here. So one thing I just maybe want to or should mention is how you would do this in practice. How do you find these directions? There are multiple ways, at least 3 ways I can think of doing that. Eigendecomposition, SVD, or you can also do constraint optimization. In any case, so if you would do an eigendecomposition, you would first construct the covariance matrix of the data. Then you would do the eigendecomposition to get the eigenvectors and eigenvalues. So you have the eigenpairs, where the eigenpair consists of the eigenvalue and the corresponding eigenvector. And then you sort the eigenpairs by the eigenvalues. And then you keep eigenvectors, with the highest eigenvalues. So these are the directions where you have most of the variance. And yeah, this is just a principal component analysis in a nutshell. There's a relationship between principal component analysis and fully connected autoencoders, which is why I was spending some time on principal component analysis. However, before we briefly go over the connection, let me introduce the fully connected autoencoders. So a fully connected autoencoder, I'm calling it like that because the layers are fully connected, like in a multilayer-Perceptron, and that would be the most basic version of an autoencoder. An autoencoder, like you can see here, there are some inputs, then there's a hidden representation, and then there are some outputs. And we call the part of the neural network that converts the input to this hidden representation, to this intermediate representation, we call this the encoder part because it's encoding information. And then we have a decoder part, and the decoder part is decoding the information to get the outputs, and the outputs, so the goal is that the outputs are matching the inputs. So you're reconstructing the data. So what you're doing is you're first compressing the data, and then you are reconstructing the data. And where it is related to principal component analysis is if this here is a fully connected layer and it's a linear layer without activation, without nonlinear activation function, and this is also a hidden layer without nonlinear activation function, then the autoencoder is kind of equivalent to the principal component analysis. So you can also use principal component analysis to reconstruct the data from the hidden representation, the compressed representation. And yeah, this would be then, so this representation would be equivalent to what a principal component analysis produces. However, it's not exactly equivalent because here we don't have an orthogonality constraint between those. So here we don't have the constraint that these are 90 degrees. They are not orthogonal to each other, these two dimensions. Yeah, and with that, that is the basic concept of an autoencoder. We have a network, neural network, that compresses data onto a smaller representation, and then we have a decoder in this autoencoder that reconstructs the data. And the loss, in order to learn that, it could be the mean squared error. So you can, if these are images and these are vectors of images, you can just minimize the pixel, so a pixel difference between inputs and outputs. So imagine on the left hand side, this is a vector from MNIST where we have the 28 times 28 MNIST images, and we reshape them to a 784 pixel vector. This would be then our inputs. Should have made them blue, so these are our inputs. And then we compress them, let's say, to 10 pixels, something like that. We can also compress them to 2 pixels, but that would be a little bit challenging. And then we go back to 784 pixels. And then for each pixel position, we would minimize the mean squared error between the input and the output. For example, if the pixel value, the normalized pixel value is 0.1, and let's say 0.3 here, then we also want to aim for 0.1 and 0.3 and so forth. So we would minimize the distance between each corresponding pair of pixels. So yeah, and that is a autoencoder in a nutshell. Also, I've prepared code examples, and at the end of the lecture we will see how we can implement that in PyTorch. It's actually super straightforward because it's very similar to a multilayer-Perceptron. Oh, I just see here in that slide I also summarized the information again that I said on the previous slide. So again, if we don't use nonlinear activation functions in the autoencoder and we minimize the mean squared error between the inputs and outputs, then the autoencoder is very similar to principal component analysis. However, the latent dimensions will not necessarily be orthogonal to each other. So these latent dimensions or hidden units won't be orthogonal to each other necessarily. So there's no particular component in the autoencoder that enforces this. And also in the autoencoder, these will approximately have the same variance. In PCA, usually the first principal component has much more variance than the second one, and the second one has more variance than the third one, and so forth. In the autoencoder, the variance is approximately equally distributed. Now that I see also that slide, it was so cluttered in the previous slide, there's also one thing I want to say here. So these here, there are multiple names for that. I mean, they all mean the same thing, but yeah, different people from different subfields use different words for that. So sometimes we call them hidden units, similar to a multilayer-perceptron. But then in the particular case of the autoencoder, we also often say the embedded space. So if you think of an embedding, so this would be the embedded space where we embed the data into a smaller subspace. And we also sometimes call that the latent space because it's kind of hidden from the inputs and outputs if it's somewhere sandwiched in between. And often people also call it the bottleneck. It's called bottleneck, I guess, because if you think of it, first of all, it kind of looks like an hourglass, right? So this is then the neck of the hourglass. And it's also a point where we compress the data. So if we go from large to small here and then back to large, then this is our bottleneck or information bottleneck where we compress the information into a smaller dimensionality, and then we can think of it as a bottleneck. We have to squeeze the data through this bottleneck. So all these are very common words for describing the hidden units here. So here at the top I also have again the loss function. So it's usually simply the squared error between a pair of pixels, and then let's say I are our pixels. We have m pixels in total. That would be the loss for one data point, for one image or one vector. And we can also average over those, so it doesn't really matter. So in that case, actually, we have to average if we want to call it MSE, otherwise it would be the sum squared error, right? And this would be also just the L2 distance. It's the same thing as this one. And this is for one data point. Of course, usually in a training data set, we have multiple data points. So what we would do is we would repeat this for all data points, and let's call them J to N. And then we can also compute the average error, 1 over N, if we have multiple data points. So this would be then the jth data pair. Okay. So that is a basic fully connected multilayer-perceptron autoencoder. So I'm calling that again multilayer-perceptron autoencoder because we use fully connected layers. Just briefly show you the connection to matrix factorization. If you have taken a computer science class, you may wonder. So if you have not taken computer science classes where matrix factorization was introduced, don't worry about it. This is entirely optional, and also you don't have to know about matrix factorization in the final exam. I won't ask about that, but just in case you're curious. So say we have the following setup where we decompose a matrix X, which is our input matrix, which has the dimensionality n times d, into two matrices, U and V transpose, where U is n times k and V is d times k, and V transpose would be k times d then, right? And here I'm superimposing this on an example of an autoencoder. So just to see where these matrices sit if we would have an autoencoder. And this matrix decomposition here, or matrix factorization here, would be a minimization problem. So where we would call that the residual matrix. And in order to minimize this, we minimize the squared Frobenius norm, just the differences between the elements in these matrices. So just minimizing the residual matrix. And for this minimization problem, we have an infinite number of optima. However, if we would then select the optimal solution that has, or there's one optimal solution where the basis vectors are orthogonal to each other, this would be then kind of similar to truncated SVD, if you've heard about SVD, which stands for singular vector decomposition. Okay. So now if I have an actual autoencoder where I have a weight matrix W, so we have then the optimal solution to the minimization problem if W is the pseudo-inverse of V. so that if I multiply W and V, I get the identity matrix, and if I multiply V transpose with W, I get the identity matrix, such that in the previous slide we had X, U, V transpose. So if I add the V transpose here in both sides, so if I add the V transpose here, I get this, and this is the identity matrix. So this reduces to I, and U I would be simply U. So we have this setting here where X multiplied with W transpose is producing U. So these together produce U. And yeah, so it will be exactly like SVD if W is the same as V transpose. So if we have weight sharing, if we share the weight between this part of the autoencoder and this part of the autoencoder. However, this is usually not done in practice. And again, yeah, just want to say this was just very briefly, optionally highlighting the connection to matrix factorization. You don't really have to follow this slide and the previous slide, because the main question is on this slide is more a general question. If we can achieve the same with PCA or SVD, which is essentially a kind of matrix factorization that is more efficient than backpropagation and support on SGD, stochastic gradient descent, why do we bother with autoencoders? Why do we care? So I can maybe answer the question for you. You can maybe think about it for a few seconds and pause the video here. But let me give you the answer. So the answer is, first of all, it was a thought exercise. Can we achieve the same thing using neural networks? And then, of course, we were talking about a very simple autoencoder where we had a fully connected layer here and a fully connected layer here with linear activation functions. However, neural networks give us power to do something more useful, or not useful, more, I would say, powerful. So what we can do is we can replace the linear activation functions with the nonlinear activation functions, and we can add many hidden layers. So we can have, I don't know, an infinite number of hidden layers, and also all kinds of nonlinear activation functions such as sigmoid functions, 10H, ReLU functions, and that allows us to make or create models that are much more powerful than simple matrix factorization techniques, which are linear transformation techniques. Now that we have talked about autoencoders, also one potential use case would be producing an embedding that we can then use for a classic machine learning algorithm. For example, we could train an autoencoder on a whole training set, and the autoencoder then learns how to represent the dataset efficiently in a smaller dimensional space. And after training, we can decompose the decoder part, so we can get rid of the decoder and only save these lower dimensional representations. We can then do that for the training and the test data set. And then we can use classic machine learning algorithms such as support vector machines, k-nearest neighbor algorithms, or random forests, and train these on the smaller dimensional representation, because these methods, especially KNN, suffer from the curse of dimensionality. SVM also to some extent, and SVM, especially RBF kernel SVM, is very expensive for large feature sets. Yeah, and I also made a code example showing you how that works in practice, where I was using the MNIST dataset, training an autoencoder on it, and then producing these smaller representations and training a random forest on top of it. I can show you this at the end of the lecture. Okay, and also similar to transfer learning, you can also train the autoencoder on a very large image dataset. Assuming you have a small dataset, you can just train it on a large dataset and then fine-tune the encoder on your smaller dataset. And for the classification layer, you can then provide your own decoder. So that would be also something you can do. It's very related to the transfer learning we talked about. Lastly, you can also use the latent space, so the embedding, for data visualization, so exploratory data analysis and clustering. But yeah, again, there are better methods for that. So one technique that is often used for visualizing machine learning and deep learning datasets is t-SNE, T-Distributed Stochastic Neighbor Embedding. And we covered that in 2018 in the classic machine learning class. If you're interested, here are some slides I made back then. But yeah, this is implemented in many packages, scikit-learn, TensorFlow. I think there's also a PyTorch implementation. And this is a technique for especially image data. So in this example, the authors compressed the 784 dimensions of MNIST onto a two-dimensional subspace, so you can see how the images cluster together. So what's nice about it here is you can see that these are the 10 classes in MNIST. That's examples from the same class. Here the digit 0, they cluster together, and also these are ones from class 3, class 1. Of course, there are outliers. You can see there are some outliers here, but overall they cluster nicely. And yeah, this is just a technique for data visualization. It's not really useful for preparing your data set for training and prediction, because it's a stochastic technique. So once you do this embedding, you cannot really do that on new data. You have to recompute it. So it wouldn't be very useful if you, let's say, embed your training data set and then you want to embed your test data set and have a classifier trained on the training embedding also perform well on the test embedding. That would not work well. So it's only really for visualization purposes. An autoencoder, in contrast, it would be deterministic. So the autoencoder, you can apply it to the training and the test data set. And also t-SNE, I would say, is still the most popular technique. It's already 12 years old, and it's not maybe the greatest technique for visualization anymore. There are other techniques like UMAP that usually perform a little bit better in practice. But again, this is only just a visualization technique, and we want to stay on track with autoencoders. So I just wanted to show you this because you may find that useful in your projects. So here I have a sketch of a very simple autoencoder that I implemented in code. At the end of the lecture, we will take a look at the code example that I uploaded here to the class GitHub repository. But let's just briefly talk about what's going on here in that figure. So what I was doing here is I took MNIST images, which are 28 times 28, and I reshaped them into long vectors, 784 dimensional vectors. And this is the same that we have used or done when we implemented multilayer-perceptrons. So here I used a fully connected layer and a nonlinear activation function, the leaky relu function. And the fully connected layer was then transferring the 784 dimensions into a 32-dimensional vector. So my embedding is a 32-dimensional vector. And then I used another fully connected layer with a nonlinear activation function to go back to the original shape, the 784 dimensions, and then I reshaped that into the 28 times 28 images. Again, the objective function here is minimizing the error, so the difference between those images, usually the mean squared error. I actually replaced the sigmoid here with a 10h function because I found that it produced better results in this particular case. However, in general, both work fine, sigmoid and 10h. You just have to be careful when you use one or the other, because remember, when you minimize the difference between this one and this one, these two have to have the same scale, right? So if you use the sigmoid function, then make sure that the pixels here are in the 0, 1 range, right? And if you use 10h, make sure the images are in the range -1 and 1. Otherwise, you will have a different scale for the outputs here, and then this wouldn't really make sense. I mean, would be problematic for the optimization then. Also, I should say some people use sigmoid, and then instead of using the mean squared error, also I often see people using the binary cross entropy. That is also another approach. Okay, so this is a very simple autoencoder. Next, we are going to talk about convolutional autoencoders, so extending the concept using convolutions. First, we have to talk about another concept, transposed convolution. So remember, from the autoencoder we have the hourglass shape where we have the bottleneck here at the center. So if we use image data, for example, an image with height h and width w, we also want to get back an image of that size, h and w. Now, if you think back of the convolutional neural network lecture, when we used convolutions or convolutional layers, we were either preserving the size of the feature map, the height and width, if we were using a stride of 1 and had the same convolution with the right padding. However, if we used a stride of 2, we were also reducing the feature map size. So how can we use convolutions such that we can make something bigger? So especially we care about the decoder part. So how can we make the small feature maps here in the center big again with height h and width w? So for that we are going to use the transposed convolution, which allows us to increase the size of the output feature map with respect to h and w, height and width, compared to the input feature map. So that will be something we will talk about in the next couple of slides, and then we will use that in the convolutional autoencoder. Yeah, and synonyms for transposed convolutions are, for example, deconvolution. And I would say that is somewhat incorrect, because mathematically deconvolution is defined as the inverse of convolution, which is a little bit different from transposed convolution. So with inverse, I mean the mathematical inverse. And then another term is unconv. So you sometimes also find the term unconv used in code examples on some papers. And lastly, another term is fractionally strided convolution. So all of them mean the same thing usually in deep learning. So in deep learning, deconvolution, unconv, and fractionally strided convolution usually mean transposed convolution, which is something we will talk about in the next couple of slides. So just to recall, here at the top I have the regular convolution that we talked about in the convolutional neural network lecture. And so the illustrations are from this really excellent guide here, which is available on arXiv, and I really recommend reading that if you would like to learn more about that, or if anything is a little bit maybe too confusing right now. So here it's really nicely summarized and described, so I really recommend this tutorial. So in any case, recall the regular convolution here at the top. So what's going on is we have this input here, so the bottom part in blue, that is our input. And then we have our kernel. So the kernel is this dark thing here, and it is sliding over the input. Here they use stride of 1 and no padding. So it will actually reduce the size of the feature map. So going from 4 to 2, because we don't use any padding here. And yeah, so when you remember, it would first compute this output, and then it would slide over by 1 position, this one, and this one would compute this part, and so forth. And then it would not slide further because it reaches the edge. If you want to maintain the output size, you would have to add padding here. Actually, everywhere. Okay, doesn't really matter. So this is just recapitulating the regular convolution. Now, the bottom part is the transposed convolution emulated with a direct convolution. So in the paper, they kind of use the normal convolution to visualize transposed convolution. So here, the transposed convolution would be going from a small input back to the original size, the output size. So in order to achieve that, you can add zeros here. So you can pad the input like this, and then apply this normal convolution to get this output here. So that would be a trick that we can use to implement the transposed convolution. Yeah, so here I have some code examples for doing that in practice. So the equation to compute the output size from the transposed convolutions would be that one. So you have the stride times the height or width. So that's either the height or the width. So if it's symmetric, it's both. So you can, usually if you have square images, you have h equals w, and this would be then the height and the width. And this would be the kernel size, and this would be the amount of padding. So with that, you can compute the output size for the transposed convolution. So in PyTorch, it's called conv transposed 2D. And similar to a regular convolution, you can give the input and output channels here, kernel size, padding, and stride. But again, yeah, you use that equation to compute the output size actually. And here I was just doing that for a very simple example, going from 2 by 2 input. So I'm doing this because remember in PyTorch they have the NCHW representation where n is the number of examples, c is the number of channels. I only have one input channel, so I'm putting a 1 for one example and one for one input channel here. And then you can see when I apply this, I should get a 4x4 output, which indeed is the case here. And here I have some more examples. So going from 4x4 to 6 to 6 and from 8 to 8 to 10 to 10. So just an example demonstrating the transposed convolution. Yeah, so what I was showing you in the previous slide was for a stride of 1. Now, what about making the strides larger? So this is maybe a little bit counterintuitive, but it's exactly the opposite compared to a normal convolution. So in a normal convolution, if we increase the stride, the output will be smaller, right? However, in a transposed convolution, if we increase the stride, the output will be larger. So we can think of it as striding over the output. Making a larger stride produces a larger output. Here in this visualization again, they are showing that concept using regular convolution. So here, using a stride of 2. Where is this? Here, using a stride of 2 is equivalent to convolving a 3x3 kernel with a 1, 0 inserted between the inputs. So they're inserting these zeros here in between. I find this, to be honest, a little bit weird or counterintuitive. So I made an alternative visualization here. So here I keep the inputs like they are. So I have a 2x2 input. And I'm applying the kernel, 3x3 kernel, with a stride of 2 again. So for the first pixel, let's make this in pink, I would have this region. And then I stride it over by 2 because I have a stride of 2. And the second one would be then this one here. For this one. So I don't know if that is more intuitive. In any case, so you can see when you use a stride of 1, you would have more overlap here. You would have the second part here. However, if you have a stride of 2, you only, for the 3x3 kernel, have an overlap of 1 row. But ideally, you maybe want to use a stride of 3. So for the stride of 3, let me clear this a little bit. For the stride of 3, I would have the first one like this, and the second one like this. So that may be better because then I don't have this overlap region here. Why is the overlap region a problem? So there was a nice article on Distill, which is a nice online journal, where they kind of visualize the issue that happens when you use strided convolutions or transposed convolutions with an inappropriate striding. So what happens is we get then these checkerboard artifacts if we're not careful. So going back, if we have these overlaps here, like I showed you before, we may get checkerboard artifacts, and that is shown in this figure here. So there's also nice visualization. So I also really recommend reading this article here. So and then images that come out of the convolutional network with the deconvolutions or transposed convolutions may look something like this, where you can see you have these checkerboard artifacts here in these regions. So instead of using deconvolutions, because it may be a little bit dangerous, you have to be kind of careful to avoid these checkerboard artifacts. Although it's not super complicated, like I said, you have to just be careful that you use a stride where you don't have an overlap. However, then also, if you are careful doing that, you may not get the desired output size. Because for this one here, I would get a 5, right, if I use the stride of 2. If I use a stride of 3, I would get 6 rows and 6 columns. So that may be undesirable. So they recommend another technique to use instead of transposed convolutions. It's nearest neighbor interpolation or upsampling. You can think of it as the opposite of a max pooling layer. Yeah, so we'll also show you a code example for the nearest neighbor interpolation. But before we get to that, one more thing about transposed convolution. There's also the padding. Previous slides didn't have any padding. So in this slide, they have a padding of 1. So it's again from this paper here. And so what happens is in a transposed convolution, if we do padding, we pad the output. Hence, if we use a larger padding, the output feature maps will be smaller because you have to kind of subtract the padding then. So again, this is maybe a little bit weird, but in the previous slide, when I showed you the previous figure, they had a 2x2, and they went from the 2x2 to 5x5 also. So here, they also have a 5x5 output. So this is the output. However, notice that they have 3 inputs now. So if you would actually apply padding of 1 to what we have seen in the previous slides with a 2x2 input, what we would get is a 3x3 output. So padding makes the outputs smaller because it's kind of like padding the output, and then you have to think away the padding on the output. It's a little bit confusing, to be honest. So in practice, if you wonder about the size of the output of the transposed convolution, you can use the equation I've given you in the previous slides. Okay, so I have 2 more code examples that I'm going to show you at the end of the lecture. So one is the convolutional autoencoder using the transposed convolution or the deconvolutional layers. So these are the transposed convolutional layers that I just introduced. And here we have regular convolutional layers. We can have 1 or more. And also we would use nonlinear activation functions and so forth, and also max pooling. We don't have to use max pooling. We can use a stride of 2, but we can also use max pooling. It doesn't really matter. I mean, it doesn't matter. It may produce better or worse results. Either way is fine. If you think back of the fully connected, fully convolutional networks we talked about in the convolutional network section, you can get better results, but you have to also introduce additional parameters. Okay, so another code example is the autoencoder with a nearest neighbor interpolation. And if you go, it's hard to see. If you go back between those 2, they both give good results. So what I was looking at the reconstructed one here. So both give relatively good results if we look at the original image and the reconstructed ones. So in that way, there's not really an advantage of using nearest neighbor interpolation in this case, but in practice, like it was described in the article, it may help with avoiding these checkerboard artifacts. So lastly, before we actually go to the code examples, let me go over some other types of autoencoders, just to round up the lecture here. So one modification we can make to the autoencoder is adding dropout layers, which can help forcing the network learn redundant features. So the network will be less likely to memorize certain pixels at certain positions. So by adding dropout, we may make a more robust autoencoder. However, where it becomes interesting is by adding dropout after the input image. So here, when we add dropout, we will drop pixels from the input image, and then when we train the autoencoder, we can implement a so-called denoising autoencoder. So this goes back to the very first application example I showed you at the beginning of this lecture, where we kind of learn how to denoise an image. So this could be by dropping pixels, but we can also add artificial noise like Gaussian noise or so forth. So but here in this case, when we add dropout, what we'll see, we have these black holes here, like black pixels. And the autoencoder is then trained by using this one here as input. So this is the input to the autoencoder. And then for the output, you compare it to the original image here, right? So that is where you still compare or compute the mean squared error. So the network only receives the broken image, but then it still learns how to reconstruct the real image by computing the MSE between the original and this one here. And again, so this would be done during training, but then in practice you may have real noisy images. So this would be a real noisy image after training. So then the network can be used for denoising images that you may encounter in practice. Another kind of autoencoder is the sparse autoencoder. So the idea is very similar to the previous autoencoder. So I was just copying my slide here. It doesn't have to be the one with dropout. The part here, so you can maybe ignore this. So the part here that is new is that we add a constraint in the bottleneck layer. So we add a L1 penalty here. And by minimizing the squared L2 norm or mean squared error between the output, so this is this part here, and the input, plus this constraint, the L1 constraint, then autoencoder learns to produce sparse embeddings here, adding sparsity to it. Yeah, so lastly, there's the Variational Autoencoder, which is super interesting, and it's a very big topic. So we could have at least 1 or 2 lectures just on Variational Autoencoders. However, let me just summarize this, or at least try to summarize this in one slide. So the Variational Autoencoder was originally proposed in 2013 in the paper Autoencoding Variational Base. And it is, in a way similar to an autoencoder, but yet very different. So first of all, the goal of that is very different. It's used usually for generating new data. So let's take a look at this step by step. So first we have the encoder part here. This is the encoder and the decoder. So the encoder is essentially a Gaussian probability density. So this would be a Gaussian probability density here. And then the output of the decoder would be a probability distribution of the data. So that is very different from a regular autoencoder, as you can already see. And the loss function is also modified. So the loss function, this is only for one data point, consists of 2 parts. So there's this part, which is the expected negative log likelihood term. So this is this part here, and you can see PW, it's this one. So it's the negative log likelihood of the data distribution here. And yeah, with respect to the encoder distribution. So the expectation is over the encoder distribution. So that is the one term. This would be forcing the encoder and decoder to produce realistic images. So the second part is this Kullback-Leibler divergence term, the KL divergence term. And this one is added to this loss function to enforce that this is Gaussian distribution here. So here we have the divergence between the encoder part and distribution, which is usually chosen to be a normal distribution with mean 0 and unit variance. So we can't really backpropagate through probability distributions. So there's a trick that this vector here, in practice there would be actually 2 vectors. There would be one mean vector and one variance vector or standard deviation vector. And we use these as parameters to the normal distribution. But this is called a reparameterization trick, but this is maybe going into too much detail right now, because like I said, we could have a whole lecture on just variational autoencoders. So, but in any case, one takeaway of that is, if you have something that comes from a normal distribution, what you can do in practice then after training is you can draw a random sample from a normal distribution and then generate an image that has not been, let's say, in the training data set. So just by sampling a random point or drawing a random sample from a normal distribution, we can use the decoder to generate new images. So in that way, it is a method for generating new data. In the next lecture, we will learn about generative adversarial networks, which can also generate new data, which are usually a little bit performing better in practice. They usually give better quality results. So in the beginning, variational autoencoders were kind of producing blurry images. You can see that even a little bit right here. So this is more blurry. It's I guess due to the Gaussian probability density, and it's also a stochastic model. However, over the years, there have been many improvements. So also nowadays with variational autoencoders, you can get good results. But I think GANs are still a little bit ahead in terms of generating good quality results. However, variational autoencoders, I find them a little bit easier to train than GANs. But let's not go too much into detail with regard to generating new data. Let us finish the slides here and then look at some code examples. So lastly, some optional reading material. I recommend, for this lecture, the deep learning book again. There's one chapter on autoencoders, and I think that's maybe a good resource to read about classic autoencoders. So now let's go to the code examples. Okay, let us look at the code examples. I prepared them, I put them on my desktop. However, they are all available on GitHub as well. Just opening them locally, so in case I want to make some comments in the code. All right, so there are 5 notebooks The first one is just a very simple, fully connected autoencoder. The second one is a convolutional autoencoder with the transposed convolutions. I call them dconv here. The third notebook is a convolutional autoencoder with nearest neighbor interpolation. The fourth one is using a convolutional autoencoder and then only using the embedding and then training a random forest classifier on the embedding. So that would be an autoencoder used for feature reduction or feature dimensionality reduction. And then lastly, if you're interested, I also implemented a variational autoencoder. But like I said, that is maybe a topic for another lecture. So we can't really cover variational autoencoders in just 10 minutes. I think that is a really big topic that would deserve or at least request more time from us. Okay, let us start with a fully connected autoencoder, one by one. So here in the fully connected autoencoder, when you look at this, everything in the beginning looks the same as before when we implemented multilayer-perceptrons. So here I'm defining some hyperparameters, and maybe the most interesting one is num hidden 1. So in this fully connected autoencoder, there's only one hidden layer, and this is the size of the hidden layer. So the size that it produces, and that is then also the embedding size. So that is the bottleneck size. So here I'm also setting up a custom transform. For simplicity we are only using MNIST, and this custom transform is first normalizing MNIST into 0, 1 range, and then this one, as we discussed in a previous lecture, will normalize the images such that they are in a -1, 1 range. I have to do this step. It's required to get the image into a tensor format. So I can't just do that both in one step. I have to do it in a two-step approach here. Okay, so that is just the setup. So by that, remember our images are now in the -1, 1 range. So this is our autoencoder here. So I divided it here into two parts, an encoder and a decoder part. The encoder part is one hidden layer and the decoder part is also one hidden layer. However, I have some stuff here I just see. It's not really necessary. I think that is because I copied it from my Multilayer-Perceptron that I had in the very beginning. So I can actually get rid of this stuff. Don't really need that. Okay, so then comes the forward method, which is actually using the layer here and the layer here. So I'm just using it here, and then also adding nonlinearity here, the leaky ReLU function. And for the decoder part, I'm using as the output activation a 10H function. So again, we don't use something like softmax because here we really want to match the pixels, right? So we want to have the input pixels matching the output pixels. And we normalize the images such that they are in the -1, 1 range. So 10H also produces outputs in the -1, 1 range. So then I'm initializing my model here. And then I'm training it. So here, the only thing to note is that I'm reshaping the images into a 28 × 28 vector. So a vector with 784 units. And then I'm using the mean squared error loss between the decoded images. So these are the reconstructed images here, and the features, which are the original images. And the rest is just regular backpropagation. And we can see that trains pretty quickly. That was trained on my other computer with a GPU. I think it doesn't take too long if I would run it here on the laptop, but I can just try in a second. So here that is how the output would look like. So it's actually not bad. So 3 looks really good. So I'm giving it the original images here just to show you how they look like. And then here at the bottom, these are the reconstructed ones. I think the 8 doesn't look really great, but there are many numbers that look actually pretty great. And all of that is based on the 32 dimensional bottleneck. So 32 is relatively small, especially if you consider this one here. It's about 20 times smaller, right? Let me just run this and see how long that would take on a laptop. Oops, I made a typo somewhere here. Okay. Okay, I didn't have the MNIST dataset here. That's actually not too bad. But again, it's a very simple, fully connected layer, so loss is decreasing. That is good. Okay, so that is the regular fully connected autoencoder. I don't think I need to wait until this finishes. Let us go on to the deconvolutional one, or the convolutional one with the deconvolutions. So in this notebook here, everything is the same. First of all, I'm not using a hidden dimension here because that really depends on how I choose the convolutional layers with the stride and everything. But again, so this setup is all the same as before. Not sure why I have model here twice. Yeah, and then the convolutional autoencoder looks almost like the fully connected autoencoder, except that I have convolutional layers now. So the encoder part is here. And I have two convolutional layers and between two pooling layers. Personally, let me shut this down. It's kind of getting loud here. The fan is turning on. Okay, so I have two convolutional layers here in between max pooling layers. And usually personally, when I do it this way, I compute how much padding I need for getting a certain output size. So I usually increase the channels, then with the pooling I decrease or usually half the size, the height and the width, and then I increase the channels again, and then I halve the height and width. And to get the even numbers, I usually compute the padding. So I usually include my computation here so that I know what padding I have to choose. It's just a personal note. I find that always helpful for myself. Then I'm using the conv transposed to D layers here. Note that I'm not using pooling layers here because pooling makes things smaller, right? Also, I could have used stride 2 here. So by the way, writing it like this is the same as writing it like this. So this is actually shorter. So I could also use a stride of 2 here and get rid of the max pooling. But also, yeah, that would make it more symmetric if you look at it. So I would have two convolutions and two conv transpose to these instead of having max poolings here and nothing here. But it doesn't really matter for autoencoders. There is no rule that it doesn't have to be symmetric. So some people say, it looks nicer if it's symmetric, but it's really not the case. You can do whatever you like. Okay, so then here is the forward method and the forward method, but the encoder and the decoder in the forward method. And I had to do some little trick because the dimensions didn't really match. So I had 2 pixels too many. So I'm cutting here 2 pixels on each side. No, actually not 2 pixels, 3 pixels. So there were 3 pixels because due to how conv transpose to D works, it didn't go really back from 7 to 7, from 7 to 7, 7 times 7 to 15 times 15. So I needed to do something here to get the 28 by 28, which we need for computing the loss. So I cut 2 pixels on one side and 1 pixel on the other side. Yeah, the training is as usual. I have my mean squared error loss here, and it's training pretty well, also pretty fast. That was on a GPU. I think on that laptop it may take 10 minutes or something. And the results, I think, look really good. If you look at this, it looks amazing, actually. But also note that now we have many more parameters compared to the fully connected one. And the embedding size is bigger. So the embedding, the bottleneck size here is 7 times 7 times 8. And before we had just 32 as the hidden layer. So we had the 32 here. So also it's a bit more, I would say, easier to learn a good decoder from starting from such a relatively big bottleneck. However, convolutional autoencoders are still necessary if you work with more complicated image datasets where you can't get away with a simply fully connected autoencoder. Okay, next one. Okay, this one is the convolutional autoencoder with the nearest neighbor interpolation, and it's the same as the one with the deconvolution, except that I'm using now the nearest neighbor interpolation. And this part is also exactly the same, the encoder part, only for the decoder I changed something. So here I only defined conv2d because the nearest neighbor interpolation doesn't have any parameters. So I'm just using them here in the forward method. So if we look at the decoder here, I have the nearest neighbor interpolation here, followed by a regular convolution layer. The reason why I'm doing that is because this is, you can think of it just as upsampling. So this is kind of the opposite of max pooling. You can also call it unpooling. And this is, not learning anything, it's just interpolating. So we need some parameters to also learn something so that the network can learn how to reconstruct the image, which is why we still use the normal convolution. But here I'm using the convolution such that I have same padding or same convolution, such that the size doesn't change. I only use some parameters that we can backpropagate through. Because, this is not really, doesn't have any parameters that we can learn. Okay, so this is yet now more symmetric compared to the encoder. It's not really necessary, like I mentioned before. However, the interpolation also works pretty well. It's also pretty fast, same runtime, and the results also look pretty great. I think they look similarly well compared to this one. I wouldn't say there's a big difference between the two. But of course, this is a very simple data set. On a real data set, it may look differently. On a dataset with big images. Okay, this notebook here is interesting. So here I'm using a convolutional autoencoder with a random forest classifier. Okay, something weird happened. I had a bug in my code, so I had to fix that before I wanted to show it to you. So I had to re-record these last 4 minutes. So in any case, we have 4 minutes left. Let me talk about the convolutional autoencoder with a random forest classifier. So everything up here is the same as before. Nothing has changed. However, I did a little restructuring in the convolutional autoencoder model here. So everything here is the same as before in the notebook 03. However, I restructured the forward method. Now I have an encoder and a decoder method here. So going back here, I put everything into the forward method. Now I restructured it and have the decoder as a method here and the encoder and the decoder as a method here. And then I'm calling those methods in the forward method. It will do exactly the same thing as before. However, there is one reason why I'm doing that, and I will show it to you shortly. So it's just a convenience for later. So the training is also the same as before. And here's just evaluating the reconstruction on the training dataset. So as before, we get relatively good results here. And then here's the classifier part. First, I'm also converting or checking the test set. So I'm also checking how the reconstructions look like at the test set. So technically that could actually be up here. So in the evaluation method. So first of all, I'm going to train a classifier on the original dataset, on the MNIST dataset, using scikit-learn. So I'm using a random forest classifier. So what I'm doing here is I'm collecting all the images. So I have a batch size of 60,000 here and 10,000. So I'm collecting all the images because scikit-learn can only work on one. So for at least for random forest, it has to get the whole matrix at once. It can't do batches. And now here I'm using a random forest classifier with 500 estimators, so 500 decision trees. If you remember that from the machine learning class. If you have not heard about random forest classifiers, don't worry about it. It's just a classifier for now, a non-neural network classifier. And on the original dataset, it gets 97% accuracy on the test set. Just something to note here. And then if I use principal component analysis, I compress the data set now onto a 7 by 7 by 8 dimensional vector. So these are now much smaller than before. Before we had the MNIST datasets with 784 pixels. Now we have a smaller representation. And PCA is a linear transformation technique. So it is maybe not ideal for images, but still training the random forest on that compressed dataset will get really good performance. So 94%. Of course, it's not as good as before, but it's still respectable. So unfortunately, PCA is not really great if we work with, let's say, real color images, for example, images of 300 by 300 dimensionality. So bigger images are usually a little bit more problematic with PCA. But here that is just a comparison. Now I'm using my autoencoder to compress MNIST. So like before, I have to compress my MNIST dataset. So here I'm using the model encoder part. And this is why I implemented the encoder as the method here. So I can call it without calling the decoder. So, okay. So this code will compress the training set using my autoencoder. So I'm calling model.encoder. And this part will compress the test data set. But again, like for scikit-learn, we need that as a matrix, which is why I'm doing this whole thing. I'm processing batches, but then I'm saving them as one big matrix, just to work around to make scikit-learn work. And now finally what I have here is the random forest classifier trained on the compressed data from the autoencoder. And what I can see is the performance is pretty good. It's not quite as good as the original performance, but again, we have fewer features now. So we reduced the dimensionality by a lot, but we still retain a lot of the useful information. So it's actually much better than the PCA example here. Also, random forest classifiers are pretty good classifiers. If you would maybe replace that with a KNN, k-nearest neighbor classifier, maybe the results wouldn't be so good, because at least for this part, I mean, because KNN usually suffers from the curse of dimensionality a lot. And also, there are many methods where we can't even use such a large data set, like the whole data set. I think even RBF kernel SVM would have problems with 784 dimensions because it doesn't really scale well to large data sets. Okay, so I think we are just about finished. So we had a lecture now on autoencoders, and next lecture we will talk about generative adversarial networks. Okay, then see you next time.